Okay, so I think we can start talking, start this lecture. Uh, the harsh time came, so I think. Oh, hello. Nice to see you. So the harsh times came, and everyone has those tasks probably all this time. So I'm also not the exception, and I have like so many things going in parallel. So like keeping this up is like really hard, but I'm not saying that we're not gonna give this lectures. Maybe there will be sometimes like last time that I'm gonna have 5 tests in 1 week which I'm not prepared or whatever, and I'm gonna just cancel the meeting. But probably, I hope that would not happen. And yeah, like I think it's the same as you have here at the university, so I think you can relate probably. So, and today is the last part of our talkie, like our section. I mean, not section, but like part of computer vision in robots. So we're gonna speak about VLMs and VLAs. So those are vision language models and vision language action models. We're gonna dive into how they work and how they're built. It's basically what we discussed before combined together, and some stuff added. So yeah, so let's like after getting familiar with CNNs and visual transformers, we are now entering a new field that's still being broadly researched, vision language models, and that's completely right because there is no like open source state of art vision language model available. There are some like models, but they're not state of art. So like it can be considered as a research model. So yeah, that's the problem, and that's like what you should be aware of. That like yeah, that's very new thing, new field, and it's developing. So what are and some information. Uh, real world is real world information is multimodal. We understand our surroundings by seeing, reading, and listening at the same time. Generating image. So like our vision models, transformers, based on transformers, can generate images, caption automatically, search for images by describing them in words, understand memes, advertisement, and infographics. And the last thing, that's our goal, like support robotics and self-driving system that must interpret surroundings and follow instructions. So I think, yeah, okay. So vision transformers only allow you to work with the images, and as you can maybe know, that LLMs allow you, like who study AI, of course they know, but like not all of my listeners here, the audience knows what are LLMs. So there's basically like chatbot models like ChatGPT. They take text as input, they give you the outputs as the text same way. So they like next token prediction thing. Yeah, it's not that interesting to be honest. So the problem with vision transformers, it's only working with the images as we described later before, and LLMs work with only text. So we combine those two things. We combine visual transformers and LLMs sometimes, and today I have prepared some example that we're not gonna use visual transformer to do image classification, but we are gonna use convolutional neural networks for that. So yeah, that's just like a thing of decision, like what would you decide to use in your model, like visual transformers or CNNs. Like you know there's some pros and cons between those two, like we spoke last time. So yeah, those are visual language models. So it's kind of yeah, VLM accepts text and image as an input and predicts the next text tokens and optionally images. So for example, I just wrote this to ChatGPT. It said like the color of the apple. I mean, the apple is green. That's like the VLM described basically. So like it works with both images and text. So here you can see some architecture of this thing, but we're gonna speak on that on like more specific example. So, and we're gonna, I don't know why I put helix here actually, because we're gonna speak about helix a bit later. Okay, so the thing about VLMs and they're like supposed to be zero-shot performance. What that means, that it should like predict something based on the images that it has never seen before. Like if you train some CNN or whatever, it train on cats, and if you put a dog to the image, like, oh, predict me what cat it is, it's not gonna give you just, I don't know, give you the wrong answer. Like, and the thing is, in Clip, it was like the best zero-shot performance vision language model, and I'm gonna try to describe how it works. So basically, how we train the Clip. So yeah, one more thing. At the top, you can see the example of usage. Like, it like predicts that that's right, like rear suspension of a motorcycle, and that's like wrong. So yeah, simple example. So yeah, we put. So at the first, we need to give two encoders, text and image encoders. That's basically like a visual language model, how they work, and that's like a training part. And we're gonna concentrate more about training here, and we're gonna talk about last function. I'm gonna tell you what is softmax. So we basically take one image, some kind of pepper the OC pop, whatever. It's like some kind of dog, and we take the image of this dog, and we put it through image encoder. You know how encoders work? It just gives you a token like of values and some vector basically, and you just put them like relatively to the attention table, attention metric. So for example, first one is this image and is the first token. So second one, and the same, like this image should correspond to that description. So here it is, like the first description and the first image. So, and it's actually, the Clip, it was introduced by OpenAI, and they use like 400 millions of those pairs, like image and the caption, and they trained some models to predict, like, it was like kind of large model, so to speak, like so many parameters, and it could predict a lot of things, like zero shot, because it was trained on like so many data. And yeah, so we built this kind of matrix, and we train our model like, so those values, because the ground truth is only on this axis, so like this image corresponding to that. For example, the next the description could be like green apple, and the next picture should be a picture of an apple. So here is the text embedding of the apple, and here is the image embedding and encoding is the same thing. So like just a vector of values, high dimension values. So they should correspond, and for example, text of per the pub, whatever, shouldn't correspond to green apple, and that's like very simply saying what is our last function. Yeah, let's move here, and yeah, our, I don't know if you remember, and we're gonna also give a specific example on that, so I hope it will be better understandable, that we should, when we train our models to predict, like with using transformer, we have this high dimensional space, and we just have each image. We had in visual transformers, we had each image, for example, image of a cat, like that's like two different images of a cat, but they should be like in the high dimensional vector, they should be like in like relatively close to each other, so they match, and so our model can say, oh, this is like a cat, and like mostly all of those cats would be in the same direction. So basically we want to do the same thing, but instead of like two images, we want to do an image and a description. So that's how we like train. So high dimension vectors should match, and like here is just, you know, two-dimensional thing, but it depends, because like usually we use those 768 dimensions in our vector, so like, and most of that we can see it's three dimension, and it's gonna be like further on you're gonna see a good representation of it. So yeah, last function. Yeah. So I want to turn on the video, and I hope it will work. I mean, who study AI, it would be probably not interesting, but this is robotics. Yeah, don't judge me.
No, we actually didn't have these models yet. I'm not aware if we have those in first. Like,
I don't think so, because there's kind of new thing.
They're too new to be included.
Yeah, and that's actually the problem of the university. Like everything is not included, unfortunately. Like everything like interesting and new is not included. Like yeah, there's no internet. So it would be much easier for me to explain it with this video. How it's all.
Loss functions tell us how wrong our predictions are.
Okay. So loss functions, yeah, that's I think how we train, and I wanted to include that thing also. Yeah.
Loss functions tell us how wrong our predictions are during training. We then use that information to optimize our machine learning model. But wait, what about accuracy, precision, and recall? Can't we just use those to figure out how wrong our predictions are? While we can use metrics such as accuracy to get an idea of how wrong our predictions are and to compare various methods and models, they often fail for use during optimization because they aren't differentiable. That is, a lot of machine learning methods use gradient-based optimizers, which just means that the function they optimize has to be differentiable in order for it to learn. Accuracy, precision, and recall aren't differentiable, so we can't use them to optimize a lot of machine learning models. A loss function is any function that is used to evaluate how well our algorithm models our data. The higher the loss, the worse our model is performing. We then try to minimize that function in order to learn how to solve the
Yeah, I
problem.
want to stop here. So the bigger that, like, think of loss as an error. Like, if the error is big, like the performance is bad.
Ask a hand.
we want to minimize this error, this loss, to make a better performance.
Most loss functions compare the predicted output with the label. That is, most loss functions measure how far off our output was from the actual answer. For example, if you're trying to classify whether or not a picture has a dog in it, your algorithm might output 0.6. After rounding, you see that you predicted this was a dog. However, during training, you're constantly trying to get better and better predictions. E.g., if something is a dog, then we want the algorithm to output as close to 1 as possible. A loss function that might make sense is to take the absolute value of the difference, i.e., the loss is equal to exactly how far off our prediction is. In the dog example, this loss would be 0.4. You then modify your model based on the size of your loss. If you have a high loss, it will change more than when you have a low loss. As a side note, it's important to choose a good loss function. If you penalize the wrong things, then your model could not learn at all, or worse, learn the wrong thing. In general, loss functions have two properties. They are globally continuous and differentiable. This basically just means that the function you use can't jump, it's defined at every point, it has no sharp turns, and no vertical tangents. A useful property of most loss functions is that they are symmetric. That is, for a loss function, the loss of actual and predicted is equal to the loss of predicted actual. Most of the time, this is nice to have since it makes sense that the loss of something being actually 0 but predicting it's 1, and the loss of something being actually 1 and...
Yeah, whatever. So this is the function that like explains the clip loss function. So okay, it looks complicated, but I'm gonna try my best to explain it. So at first we have softmax. So what is softmax? It's basically thing that like normalizes out our output of the model. For example, when we put some when we get like I already spoke on that, but I don't think I explained it very well last time. But I mean, hopefully it's gonna be better now. So okay, I don't need to write anything. So for example, when we give some training data to our model, so it predicts, like for example, this is a dog. For example, this was the image of no, we put one image, and at the end, our model, before this last function is implemented, it gives some like predictions. So for example, it gives instead of in one thing of it, for example, we gave the picture of a dog, and it gave like 30% to a cat, like 90% to a dog, and I don't know, like 80% to a crocodile. I don't know, whatever. So after softmax just it's like summing up those things and dividing them by the amount of things we got. Am I right? I guess. So basically we have like this thing here. So this is the output of our softmax. For example, for the first input gets us 0.2, 22%, 40%, 36%. So our model is kind of weak. For example, if we got, this is the ground truth, for example, output, the dog, which is intended, and if our model predicts 90 but like less here, that would be better. Like, and we can make some like predictions on it based on it, but it kind of and yeah, the model needs to learn these things. So yeah, this is like just basically what I've described, and we can tune this model using temperature, and I think I've implemented here the example, the temperature. Yeah, okay, it's gonna be seen later. Okay, so this is like just the output of softmax after after our softmax, the prediction of our CNN. So here, the part with E, basically. Yeah. So the first softmax function which we do here, it's prediction of our image on our text. So, for example, giving some image. For example, this one. This is the image embeddings. So basically, the first loop checks for those images, and it like relates to every text embedding, and it gives us this softmax output of like multiplying everything together. And for example, here should be like 0.9, and here should be like less. Like these things they should be less because they are like not our dog intended. Like this is our intended thing. So here should be less, but we don't know if our model predicts this right or wrong. So we train it like using this softmax. Yeah, and we do the same thing with text. We compare if this text one like relates to the image just correctly. It should only relate to the first image, and the next images should be like less, like 0.01 or 0 would be perfect. And like this is our loss function, and we just yeah, so this is like image compared to text part, that one, as you can see here, image compared to text, and text to the image. We also divide here at the front by 2 because we have like 2 values, and we should take the average loss function, and we just take the log because higher probability means smaller loss. That's what I showed you at the video. Like that's basically why we use logarithm. And yeah, I don't think it's like extremely important to know this. Like if you're not gonna be some researchers, I don't know, maybe you're gonna be one, you'll need that probably. But like if you're only gonna use like in some everyday tasks your VLA model, you're probably not thinking about it. So yeah, and oh, I wanted to show this video. Okay, instead of probably
gradient
like,
descent
okay,
is the process.
It's the same like as loss function. Like I don't know. Let's look at it.
By which machines learn how to generate new faces, play hide and seek, and even beat the best humans at games like Dota.
So you get the better like
What exactly
understanding
is gradient
if you're not AI student.
To answer that question, let's say you're trying to train your computer to listen to an audio file and recognize 3 spoken commands based on a labeled dataset. The first step is to formulate this machine learning task as a mathematical optimization problem. For example, you can work with a neural network whose weights are unknown variables, whose input is an audio data, and whose output is a vector of size 3, where each entry represents how much the neural network thinks the audio corresponds to each command. Then, for each example in the dataset, you compare the output of the neural network to the ideal output. Take the difference, the square, and then the sum, and you get the cost of a single training example. By taking the sum over all training examples, you get the overall cost function. And the problem
Yeah, here it was like a little bit easier, not some softmax, but you get the idea. You just sum up and
now becomes, how do we find the right value of theta that makes this cost function as small as possible? And this is where the second step, or gradient descent, comes in. And you might ask, why do we need to invent an algorithm for this at all? Can't we just plot the function and point to the minimizer? Well, theta usually has many more entries than just two. And in that setting, it's hard to see what the function looks like. So what can we do?
yeah, and here comes the part that I couldn't understand from this video. Like,
The insight of gradient descent is that while we cannot get a look at the whole function all at once, we can easily evaluate the cost function at an arbitrary point. And with a process called backpropagation, we can also evaluate the negative gradient of this cost function and take a small step in that direction.
I mean, we have this loss function. I don't understand like this gradient loss, and we are like making those little steps to get to the ground truth point, the lower point. But I can understand why can we look at whole function at once and just predict the best value of this last function. Maybe some of you.
Yeah, so the point is that this function is very, very complex.
Oh yeah, that's like
yeah,
because of the dimensions.
Yeah, because of the dimensions and because it can be like have very different shapes. So it
Okay.
can be smooth in some area and very sharp and fast changing in other area, and we don't really know where is which type.
Okay.
And which value, so we only know these places that we can calculate, and we calculate like using this neural network basically.
But for example, we have like this function, like it's 2D, but you understand what I'm talking, like 3D. For example, when we start here, we are dropping down like to this point. Why we don't just go here? Like how should we predict that there is a better answer like here instead of here? Because it's like if you look locally, like if you go right, it's like larger, it's better, it's worse, and it's like how do we know like if like that? I mean that there are some tricks to like do that, but like how can we?
Yeah, so we actually don't know if there is any better point.
Okay.
And we just have this like functions that try to check around and maybe check around this like
So we
peak
like
that
put
we have near.
different points.
Yeah, and
different
we,
places. And for example, if it's found here, that's
yeah, in
okay.
near this point, so we have different points around this point that you marked first,
Okay.
and we try to check if there are some like lower points behind the hills, but we don't really know if they're hills or not.
Okay.
So the point is that we have some smart functions that try to check around and find, and if we have the slope, then if the slope is going down, then we go in this direction and hope that there is the best point.
Okay.
So there is this like exploration against the best local.
Okay. Thank you for explanation. Yeah.
Gradient descent
Interesting to listen to.
continues in an iterative fashion. It computes the negative gradient at the new point, takes a step in that direction, and so on and so forth.
Yeah, like
The intuition behind every step is that the gradient of a function gives you the direction that increases that function the most. So by taking a small step in the opposite direction, you can hope to make the function decrease at each iteration. Gradient descent, as I just presented it, is known as vanilla gradient descent, because several variants have been developed throughout the years to improve it. In stochastic gradient descent, instead of taking the sum of
okay,
all
it's got too complicated, I think. Okay, so what I want to show you is this thing. I hope it can be. Wait, we can do it actually better. А, не чекай, because I want to show from my laptop, because like I have a problem with HDMI. That's why I'm using my friend's laptop. So sorry for that inconvenience. Yeah, that's the only way. Yep, that's the only way how to deal with it, I guess. Yeah, okay. It's I cannot do better, fortunately. Okay, so we've got some. Actually, it was stealed from like that. There's a model called Nano VLM, and I basically stole it from there. There's like this description. There's a guy who told like how it works and how to implement it. So basically, I just did that, and I'm just gonna show you how like those things work. And what did we do? We just we are gonna train this visual language model. So what are we gonna have? We are basically gonna have some images. Imagine like frame. We're gonna have few images like square, circle, and triangle, and we are just gonna put them to the different sides of an image, and we are gonna and then we are gonna try to train on it on like synthetic data and predict on the same synthetic data, and like just to understand what kind of parameters we can use to train our model. So okay, it's probably seen here. I'm gonna check if it's seen from here. Yeah, it's okay. It's all right. So okay, so the first thing we need to import something. So at first thing, most important thing that you're gonna work when you design some visual language models and generally some AI models, it's like Torch, like the libraries from Python, like Torch, NumPy, and here we actually used some math, some PIL, some matplotlib, but it's not that. It depends on use case, so it's not that unique. So, okay, and we have those global variables that we have defined. So, device is basically like the device we are gonna compute all of the things. So, it's usually set to CUDA, if you have CUDA, but most of the time people don't, so you use GPU or CPU. Image size, the dimension of our image we're gonna feed. The embedding dimension is the dimensionality of the learning embeddings for both images and text. So it's like basically how many dimensions our vector has. So attention head is quite interesting because like I don't know how to explain it bad, like in a good way, so I just wrote some notes. How much details do we want to learn? Like the more attention heads you have, the more like differentiable your image prediction like VLM would work like in like kind of different ways. It can predict a lot of things if you do a lot of attention heads. That's what I understood while trying to get it understood. Yeah. So the batch size is like data pairs. So when we when we train our VLM model, we have like image and we have the text embedding to it, and we have like few hundreds of them. So that's like the batch size, and we have some epochs. Is that just basically how many times we're gonna go through the training loop? It's not that important. So the temperature of our softmax function, the t value here at our function. So we're gonna try to change those things, and yep. So just basically, I'm gonna quickly go through all of the code that is presented. So we have like different color shapes and positions, like the defining our data set. We have some drawing function that's just gonna draw our images. It's like I'm gonna send this file to you, so you can dive deeper if you want, but it's kind of boring me explaining here. So here we just assign we're just making a class that's gonna have like some images, some captions, and yeah, there's gonna be some function that's gonna encode them and stuff like that. So iterating through all of the combinations here, as you can see, some function definitions, some encoders, and we're gonna build those with vocabulary. So okay, this is the train loop. Yeah, sample data visualization. This is basically how our image is looking like. The purple triangle bottom left, and you can see it here. Encoder, image encoder thing, text encoder class, and complete last function that has been like told here, but they use a bit more complicated thing called cross entropy. That is also including softmax function, if I remember well. Yep. Basically I think it's just more a bit complicated version of softmax. But I'm not sure, to be honest. Maybe some of you knows what is cross entropy.
Yeah, there was something like that.
Yeah, so it's but basically the last function. Like, think of it like a last function. You actually don't need to. I mean, it would be good if you know like deeper, but whatever. Who cares? And yeah, image, some optimization, some helper function is gonna show images, pre-train, embedding visualization. So we are gonna see before training and after training, and some epochs running and stuff like that. So okay, whatever. I'm just gonna try to run it all at once. And you're gonna see like what are we doing while training. So I'm gonna show how the image predicts at 0 shot before training and after training. It's gonna be so this is our image, red square bottom, but it's not yet predicted. Like, nothing is predicted yet, so we just have this image. This is our image embedding. All of those things, all of these colors represent some high dimensional vector. Think of it like RGB, for example. Think of like I told you that text embedding and image embedding vectors should be in one direction. So think of it like if they're same color, they're in the same direction. Think of it like 3D space in RGB. Like if two vectors are close in RGB, they are more or less same color. So it's basically the representation of that color representation. We can ask Gemini here, I guess, to make it 3D, but let's bother with it later. So some training thing, and after training, our VLM model. Let's. Okay, I'm not gonna dive into training part, to be honest, because I want to concentrate also on VLAs today. So this is post-training thing. Basically, what we do, we just put through this last function. We make some. We tune our model, and we get this output. This is the prediction. As you can see, the vectors relation it's kind of better here. For example, here it's yellow, yellow. It's kind of dark blue, not that dark blue, but still dark blue. But what if we change some parameters? Like, if you can see here, it's like totally random. What if we change some parameters? For example, if we choose not 4 attention heads, but like 1. I hope it will run. Yep. It should be simpler to compute, but yeah, as you can see here, because we used 1 attention head, we didn't get so many details. While, but no, actually it's not that bad. Okay, because our image is quite simple, pretty simple, so it's like did a pretty good job. What if we do like attention head? How much details do we want to learn? And the thing is, it should be divisible. The embedded size should be divisible by that. So like 64 divided by 64. 60, for example. It should be like better, I guess. I mean, yeah, it's, at some points it's better, it's at some points it's not, but actually, so depends. Okay, whatever. Let's take a look at, if we take one epoch, if we change only once. No, wait, okay. Let's change our dimensions of the vector that represents the whole image. If we're gonna do it like 3 values, and we do like, because embedded dimensions should be divisible by this, so it should be like 3, I guess. Yeah. It should be a, yeah. As you can see, it's quite poor at training, so it was like this. It didn't change much because we put too low amount of embedding dimensions. So if we do like 9, there will be like 9 vectors, 9 dimension vector representing our image. So it should be like a bit better with predicting. Yeah, I mean it's not that good actually because we put like so small attention head, but it looks better. What if we do like 9 attention heads? Okay, I think it's better. Yeah, and just this is how we train, how we do these things. I mean, I just show it here just to show you the representation. I'm gonna send you like those materials where I get it from and this code, so you also can look at it if you are interested in it. And yeah, I think we're done here. Also, the vision language model, the vision language action model, actually the most interesting part about robotics and where it's used, how it works. I'm just gonna give you a example based on figure and how they solve this vision language action model for robotics, and I'm just gonna show you the video.
Hey figures, can you come here?
So those like brain inside those things, those robots are just VLAs. So like there's no magic, nothing, just VLAs.
Okay.
It's quite simple with vision language models, but they're quite different. Because we are also not predicting also the text of an image. or image based on text, we predict the action. We predict the movement of the robot, and it's very important how do we train it, because at this VLM example you saw some image predictions and how it's good predicting the image, but at VLAs, what we do, we train our robot on, it's probably like trained, I'm not sure about that because I mean I don't work with those robots, but I think it's trained or there was this kind of learning, oh my god, it's just how it was, like supervised learning. So it's probably like how they collected this data about, like, the robot sees something and it should move here. So they probably took some picture and they moved the robot hand, like by the hand. Using encoders from the robot wrists, they wrote this data into a vector, like how much every rotor turned, and they just made like a big data of it, and maybe that's how they are trained it, but I'm not sure actually, because they are not open source. I cannot look up for it because like not everything is open source and you cannot look up at everything. So that's how it works. You probably saw it, but
even though this is the very first time that you've ever seen these items, I'd like you to use your new Helix AI and try to reason through where you think they belong in the scene, and then work together to put them away. Does that sound good?
this is zero shot. Like, it never seen such a objects probably on training as they claim, but it works somehow, like using VLAs and this transformer approach. And also because they're using transformers, they're also slow, but I think they don't compute it like on edge. They don't compute the images on the robot itself. They probably don't have like graphics card built in, but maybe they have. Like, we don't know. It's not open source because it's so much data to compute, and or they use like extremely expensive like graphics cards. I don't know how they power them, but like, okay, this is the question that's open, to be honest. I'm not sure if they share this or not. Yeah, and this is not teleoperated how the Neo is as you, if you remember in the last thing, the figure is the most advanced thing, the most advanced robot right now. Yeah, this is basically how they work. You can look up for this, and what I'm gonna say, it's how they work. Maybe you read a book like Slow and Fast Parts of Our Brain. I'm not sure. Yeah, Thinks Fast and Slow. I actually read this book, so there is like describing that our brain has like two parts of